Okay, relativity. You know, when I was looking for a way to introduce this subject, I did a search for a cartoon that might illustrate relativity, and I got this one. So a family's gone to the zoo. They're enjoying the day. It's a beautiful sunlit day, and the animals are happy, and everybody's happy. They're holding hands, and they're looking at the hippos, and the hippos, nice quiet day. Hippos are yawning, and the fellow looks at the hippo yawning, and he thinks, just remembered, your mother called today. That's relativity. I think the day's going to change right after that. But consider this. Earth is spinning around on its axis, and we consider ourselves to be at rest, but actually we are moving. True reality is quite different from what we think. In fact, if you were at the equator, you would be moving at more than 1,000 miles per hour, because the equator is 25,000 miles around, and we go around once every 24 hours. So, at the equator, 1,000 miles per hour. Anywhere else, still pretty fast. That's nothing if you look at the solar system. The Earth is revolving around the Sun at 30,000 meters per second. And this is a picture of the inner solar system. So you have the asteroid cloud, which is the green part, green toroid on this picture here. 30,000 meters per second is 67,000 miles per hour. So we're going around the Sun at 67,000 miles per hour. That's nothing. The Sun is orbiting the center of the Milky Way at 250,000 meters per second, or about 560,000 miles per hour, more than 500,000 miles per hour. Even at this speed, it will take about 220 to 250 million years for the Earth to go once around our galaxy, once around the Milky Way. That's almost one revolution for the dinosaurs. The dinosaurs lived for 180 million years, so they almost made it through one revolution. Maybe they hit one spot that was really bad, and maybe that's why they went extinct. 560,000 miles per hour. That's pretty fast. Here's a picture of the center of our solar system. You can't see the black hole at the center, but you can see the effects of it as these stars are moving quite rapidly around the center of our galaxy. That's still nothing. The Milky Way is one of 10,000 galaxies in the local supercluster. We are being pulled in the direction of the constellation Centaurus at the speed of 1.25 million miles per hour. Relative to the background separation of galaxies and clusters, this is not even significant. The rate of space being manufactured between galaxies ensures that galaxies are receding from each other at between 10 million miles per hour and 40 million miles per hour. Wow. Now note that the speed of light is 670 million miles per hour. So it's still a little bit faster than that. So what does all this mean? Well, we think we're at rest, but actually we're moving quite fast in many different directions. And yet our reality seems somewhat normal. Since the universe is mostly space, we're going nowhere really, really fast. So why isn't our reality changing, or why don't we see the effects of all these velocities? And maybe we do. It's a good question. So it comes down to relativity. And we go back to Isaac Newton. Newton believed in absolute space, but he also recognized that one cannot chart the motion of a body through this space. Instead, we define the position of one body with respect to another, relative to another. The way he stated in his great work, the Principia. And so, instead of absolute places and motions, we use relative ones. Even back then, when Newton was presenting his great work on physics, he realized that we had a problem with this idea of relativity, relative motion. We define what is called an inertial frame of reference. The laws of mechanics are the same in all inertial frames of reference. The frame of reference is not accelerating in an inertial frame of reference. So objects subjected to no forces will move in straight lines at constant velocity in an inertial frame of reference. Here's how it might work in Galilean or Newtonian relativity. Say we have a woman throwing up a ball in a plane. Need something to throw up. And it goes up, it comes down. She throws up the ball, it goes straight up, comes down, it seems to move in a vertical path according to gravity. And this is the same motion as it would have if she were standing on Earth at rest. So the law of gravity and the equation of motion for uniform acceleration is the same in both reference frames, even though she's moving at constant velocity to the right. All right, let's say we had a stationary observer and somehow he could observe inside the plane through some hole in the fuselage of the plane. Now he would see that the ball that she's throwing up is not just going straight up and down, it's actually going through a parabola as she throws it straight up and down because of its velocity to the right. So he views the motion of the ball as a parabola. And has a velocity equal in the horizontal direction to the velocity of the plane. Unless the ball leaves her hand, gets stuck in the cockpit, starts moving around, starts interfering with the function of the plane, and then the plane changes direction and starts moving in a different direction. But we're not going to worry about that. Okay, so strike that. That's not going to happen. All right, so the conclusion is the observers disagree on the shape of the path of the ball, but they both agree that the motion obeys the laws of gravity and Newton's laws of motion. And they both agree on how long the ball is in the air. So, conclusion. In Galilean or Newtonian relativity, there is no preferred frame of reference for describing the laws of mechanics. We could use either frame of reference, and we can use Newton's laws, and they will apply either in the plane or on Earth. There are some limitations to Newtonian or Galilean relativity. Galilean relativity only applies to mechanics, and it only applies to inertial frames of reference. Galilean relativity does not apply to experiments in electricity, magnetism, and optics. We have problems there. Let's see what might arise in terms of this. Let's say we have a passenger in a train, and he has a flashlight, and he's going to turn the flashlight on, and so there's going to be a pulse of light, and that pulse of light is going to travel through the train from one end of the boxcar to the other end. The observer S outside the train should observe that the speed of this pulse would be the speed of light plus the velocity of the train. The two velocities, according to Galilean relativity, should add, and the combined speed will be the speed that she observes. However, we find that in reality, if she measures the pulse of this light, she would also measure the speed of this light to be the speed of light and nothing more, nothing less. So why don't these speeds add? Why doesn't she observe that the speeds add and go indefinitely to a higher value? That's a good question. We hope to answer that in just a moment. Consider this. All waves that we know in a mechanical sense need a medium to propagate. Waves on the water need water. Sound needs air. And so they need a medium to propagate through and get from one place to another. For a long time, it was viewed that light should need a medium as well. Shouldn't electromagnetic waves need a medium to propagate? Maybe, maybe not. It was proposed that the luminiferous ether was this medium that allowed light to propagate from one point to another. This medium would be massless but rigid enough to allow light to pass. It could have no effect on the motion of planets or other objects, because that was not observed. But there should be an ether wind as planets move through it. Because planets are moving, as we just talked about. The Earth is moving around the Sun at 30,000 meters per second. So if the Earth is moving through this luminiferous ether, then that speed should have an effect on the speed of light. Well, in 1887, the Michelson and Morley designed an experiment, and they had a setup that looked something like this. A light beam goes through a beam splitter and reflects off two mirrors and comes back and interferes on itself. This kind of setup is called an interferometer, and it allows the light to interfere on itself, giving an interference pattern. So you set up this interferometer. You see this interference pattern with respective constructive interference and destructive interference, like the pattern that's been shown on the left here in red. So if you were to move this whole experimental setup, it's on some kind of platform, some turntable, and if you were to move it without moving anything else in the setup, the light source or the mirrors or anything else, just move the whole setup, then there should be some point where you encounter the ether wind. Either you're going with the wind or against the wind. You're just changing your orientation with respect to the way that the Earth is moving around the Sun. So they rotate this whole setup 90 degrees, and they found that the interference pattern did not change. And you would expect that if the speed of light changed in any way possible, this interference pattern would change as well. No fringe shift of the magnitude required was ever observed. They got a null result. And they did this at 90 degrees. Eventually they did it at 360 degrees. Rotate the whole apparatus all the way around, saw no change in the shift pattern. Implications. Light is now understood to be an electromagnetic wave, which requires no medium to propagate. This idea of a luminiferous ether was discarded. Also, the laws of electricity and magnetism are the same in all inertial frames. The addition laws for velocities were incorrect for electromagnetic waves for light. So, great results for this experiment. Michelson became the first American to receive the Nobel Prize in Physics in 1907 for basically seeing nothing. Here's Michelson sitting in his easy chair. He's just, pretty happy with this experiment results, even though he saw nada, he saw nothing. And they thought, well, that's okay. Here's your prize. So they give him the Nobel Prize for seeing nothing. Yippee. But you know what? After he got the Nobel Prize, he continued to try to refine his experiment better and better and better, using more and more interferometry, rotating 360 degrees. He tried harder and harder for the next 20 years to see if he could see any change in the fringe pattern. So basically, he continued working on a project which, if he did see a change, would invalidate his Nobel Prize. And they'd have to come in, if he ever saw something, then they'd have to come in and maybe take it away. Fiddlesticks. Nah, give it now. Okay, take it away. But he never did see anything. So he basically just confirmed what the Nobel Prize had said, is that there was no ether for light. Consider this. Let's say you were to jump off a cliff. You're Wile E. Coyote, and you jump off a cliff, and you fall under a force equal to gravity. Okay? And you do this for a time of 1 year. How fast would you be going after 1 year? Good question. Okay, fall under gravity for 1 year. What would be your speed? Well, if we were looking at Newtonian kinematics, first equation of kinematics is your velocity is equal to your initial velocity plus acceleration times time. In this case, we start from rest. So our velocity would be equal to the acceleration of gravity, g, times the time of 1 year. G is 9.8 meters per second squared. The time of 1 year, you learned in day 1 of Physics 1, is approximately pi times 10 to the 7 seconds in 1 year. So this is approximately equal to 3 times 10 to the 8 meters per second. If you fell for 1 year under the acceleration of gravity, at the end of 1 year, according to Newtonian mechanics, you would be moving at 3 times 10 to the 8 meters per second, which is indeed the speed of light, which we designate by c. So after 1 year, you'd be going the speed of light. How about that? How fast would you be going after 2 years? Well, if Newtonian mechanics were correct, you'd still be falling under the same acceleration. After 2 years, you should be going twice the speed of light. Yeah. Speed's a problem. If you actually conduct high energy experiments with small particles, you find that these particles quickly approach the speed of light. So you just give them a little bit of energy and they're flying. And they're going near the speed of light automatically. So you give them more energy and you find that they get closer to the speed of light, but they don't quite go beyond, they don't ever go beyond it. You give it more and more energy, just pour the energy in, and they still only get closer to the speed of light. They never go beyond it. There seems to be a speed limit to the universe, and that seems to be the speed of light, 3 times 10 to the 8 meters per second. So the speed of every particle in the universe always remains less than the speed of light. Newtonian mechanics puts no upper limit on speed, so in Newtonian mechanics, it really never had to deal with problems of this nature, but it's assumed that you could keep on adding speeds and things would be okay. It's in contrary to modern experimental results with fast-moving, high-energy particles. So, Newtonian mechanics becomes only a special case, a slow case, of Einstein's theory of relativity, special relativity. Albert Einstein. Let's look at Einstein. Here's a picture of him. 1879 to 1955, so I guess he was, 76 years old when he died. In 1905, he published 4 papers. 2 of them were on special relativity. The other 2, one of them was on Brownian motion, and the 4th one was on the photoelectric effect. any one of these four were so fantastic that he probably could have won the Nobel Prize for any one of those four very short papers. It's probably the greatest year any theoretical scientist has ever had. These four simple but profound papers he published in 1905. In 1916, he published about general relativity. He received the Nobel Prize in 1921, and even though special and general relativity were fantastic theories, he got the Nobel Prize, at least the way they worded it, for this one paper on the photoelectric effect in 1905. So they say, and your contributions to theoretical physics, but they're theories, so it's kind of hard to give the Nobel Prize for that. So he got it for the photoelectric effect, which we'll talk about later. He continued to search for a unified field. He wanted to combine electromagnetism and gravity and the strong nuclear force into one force, one unified field governing the whole universe. Never quite found it, so he died before he was successful in working on that. Searched his whole life for a good hairdresser. Never quite found one of those either. Here's Einstein's principle of relativity. Only two very simple postulates. The first one is the principle of relativity. And it goes like this. All the laws of physics are the same in all inertial frames. Very simple statement, but very profound, and stating something that's very nice to know. That all the laws of physics are the same in all inertial frames. We change our inertial frame, we don't expect anything to change as far as the laws of physics. Cool. So this includes all laws, not just mechanics. The results of any kind of experiment performed in a laboratory at rest must be the same as when performed in a laboratory moving at constant speed past the first one. No preferred inertial reference frame would exist. And it would then be impossible to detect absolute motion, because who is the one moving in absolute motion? Who's the one absolutely at rest? How do you know? All the laws are performing the same in all inertial frames. Cool. The second postulate is pretty simple as well. The constancy of the speed of light. Speed of light in a vacuum has the same value in all inertial frames, regardless of the velocity of the observer or the velocity of the source emitting the light. The speed of light is constant in all inertial frames. Wow. Pretty simple, but pretty profound. This has been confirmed experimentally in many ways. The speed of photons emitted by particles traveling near the speed of light have been measured to be the speed of light. So even though they're near the speed of light, emitting light that's traveling at the speed of light, the speed of that light is not twice the speed of light, it is the speed of light. So in general, relative motion is unimportant when speaking of light. Light is the same speed in all inertial frames of reference. Nice to know, a simple constant, and it allows us to think of the universe in a more simpler way. There are some immediate implications of these postulates. It solves the contradiction between Galilean relativity and the observational fact that the speed of light is the same for all observers. So we don't have to worry about this problem they were having with the speed limit of the universe. We have a speed limit. Maxwell's equations need not be changed, and this was probably the impetus for Einstein to conclude as he did, or to think along these lines, because he loved the Maxwell equations. They're so simple, they describe electromagnetic phenomena, they They just use simple mathematical operations like the curl and the divergence, and they're just beautiful. And Einstein believed that this beauty must be pervasive throughout the universe, and explains this null result of the Michelson-Morley experiment, that there is no luminiferous ether. So, it keeps the beauty of the universe. It keeps things simple. There are only two very simple postulates. What could go wrong? Well, if we accept these postulates, then we do have to change our thinking in other ways. We must alter our common sense notions of what is space and what is time. In particular, it's going to change simultaneity, the simultaneous expectations of two observers. Consider this. We have a thought experiment. We have a boxcar moving with uniform velocity. It's moving with uniform velocity to the right. And two lightning bolts strike both ends. The lightning bolts leave marks. So we're going to have a strike here at point A prime on the boxcar, and simultaneously, if you will, it's going to leave a mark at point A. And it's going to strike point B prime on the boxcar and leave a mark at B as well, because they're at those locations at that moment. We have two observers as well. We have an observer midway between these points, one in the boxcar and one on the ground. So we have O prime in the moving frame of the boxcar and O on the ground. Great situation. Lightning bolts hit both ends of the train. Two observers to observe these lightning bolts. What can go wrong? Well, the first thing in conducting the experiment, neither observer is really taking note of the fact that they must be in a very terrible lightning storm, with lightning hitting the front of the train and the back of the train, and yeah, we knew that was going to happen. Lightning could even hit one of the observers. Well, let's think past that point. Let's get back to the point where lightning has hit the front and the back of this train. What are the woman's observations? Well, these lightning bolts hit point A and point B, and immediately the information of those strikes starts traveling towards her at the speed of light. So, point A and point B are equal distance from where she is, and those light signals that will give her the information that she needs to learn about those lightning strikes will arrive at her at the same time. So she will conclude that these lightning strikes were simultaneous in her frame of reference. So she concludes the light travels the same speed or the same distance. She concludes that the strikes were simultaneous. But what about the moving man observations? The lightning hit B prime and the lightning hit A prime, and the information of those strikes start traveling towards him at the speed of light. But the information that is struck B prime hits him before the information that is struck A prime, because the train is moving to the right. So, even though they moved from B prime and A prime at the speed of light, he's been moving forward, and he's going to hit that information from B prime first. The two observers must find that the light travels at the same speed. So in his observer, light does travel at the same speed. He concludes, since he received information from B prime first, that the lightning struck the front of the boxcar before it struck the back of the boxcar. So in his frame of reference, which he has no idea that he's moving with respect to someone else, in his frame of reference, the two strikes are not simultaneous events. Well, they're both all right. The two events that are simultaneous in one reference frame are not necessarily simultaneous in a second reference frame. And in fact, they would not be if the second reference frame is moving relative to the first. So simultaneity is not an absolute concept like we've grown up to feel like it has. We always feel like things are simultaneous if they happen in front of us at the same time. Not an absolute concept, but rather one that depends on the state of motion of the observer. In this thought experiment, both observers are correct because there is no preferred inertial reference frame. So we have these beautiful concepts, these beautiful postulates of relativity, and now they're taken away from us simultaneity. That's one aspect. We're going to end our first lecture there and go on into time